of the RGMC 2025 competition, which is held during the ICRA 2025 at Atlanta. Our team, JVDF, is from Department of Automation, Tsinghua University. Our presentation will have the following contents. First, we are going to introduce our team. Then, we are going to explain our technical approaches. Finally, we are going to introduce our lab. Our team is from Department of Automation, Tsinghua University. The advisor of our team is Professor Xiang Li, who is an associate professor in the Department of Automation. And the students are also from Department of Automation, consists of 4 undergrads, Chen Dongxing, Zhe Feng Zhang, Gong Rui Ma, and Shihefeng Wang. First, we are going to start our technical approaches explanation from the solution pipeline. The task of this competition is defined as follows. The task consists of the final phase of stage 3, which is pick and place of sequential objects in a cluttered environment. The task has 20 objects from the CEPB dataset, which is a combination of subset 1 and subset 4. So our solution pipeline starts with the grasping sequence. If the grasping object is visible, then the grasping primitive will proceed. First, we use the RGBD input to detect the object. And then we will choose among 3 grasping methods, which is grasping with parallel gripper, or using the suction, or using an electrical magnet. And then, correspond to each grasping method, we will generate the grasp pose and do motion planning and executing. If the grasping object is not visible, then we will skip it or using some decluttering strategies. After executing of grasp primitive, we will check if the grasp was success. If it's success, then we will move on to the next grasping object in the sequence. And then we will introduce our custom designed gripper. This is a hardware overview of our system. The hardware consists of the following components. First, it's a robotic 2F140 gripper. Then, it's a multi-layer silicone suction cup. We also have another end effector, which is an electrical magnet. So these are the 3 end effectors of our robot. And then we have a RealSense RGBD camera. Finally, we use the telescopic rack mechanism to move the robot end effector. This is our control system architecture. It features hybrid communication framework. We use official ROS driver for the robotic gripper and RealSense camera. We use CAN bus network for the suction and an electrical magnet and also the rack. It also features decoupled system components. Also, we use heat dissipation design. And as you can see in the isolated control box, we have a maintenance advantages because the box is conveniently disassembled and assembled. These are the demos of the 3 grasping methods of our robot. In the left is grasping Cheez-It with a suction end effector. In the middle, it grasps a glove with the parallel gripper. In the right, it's grasping a key with the electrical magnet. Then we are going to introduce our perception and planning algorithms. For detection, we use a model based on YOLO V8. Our dataset is self-collected and self-annotated. We annotated the exposed part of the partly occluded objects so that the model can detect them, even if they are not fully revealed. And we use only shorter than 30 minutes for data collection, annotation, and model training for the novel objects. The functionality of this model is pretty well. It has highly precision object detection, even when only a small part of this object is exposed. For segmentation, we use the mobile segment anything model, which inputs an RGB image and a bounding box, and it will return the object segmentation mask. It also uses the segmented image to extract the object's point cloud. Different pipelines are used among the three grasping methods. For grasp, we input the point cloud to the AnyGrasp model, which outputs multiple grasp poses. And for pose selection, we first use collision detection to remove those poses which are in collision with surroundings or other objects. Then we choose the best pose among the rest of them. For section, we input the cropped RGB image and also the depth image to the SectionNet model, which can output multiple section poses. We also choose among them and get the best grasping pose. For the magnet method, we just input the bounding box center, which can be generated by the object detection model, and use the center as the grasping pose. We also design special methods for section. The purpose of this design is to avoid collision with the box when using the section method. This collision is caused by the asymmetric gripper that we designed. And also, the special method can simplify the motion planning by manually modify suction pose and the end effector joint angle. In detail, the box is divided into 4 areas, and in each of the areas, we manually adjust the joint angle of the end effector before we use motion planning to plan the trajectory for the robot to get suction poses. Then we will introduce our grasping and decluttering strategies. We classify objects into 4 categories. The first one to the third one are objects that can only be grasped by the gripper or the suction or the magnet. And the fourth category is objects that can both be grasped by the parallel gripper or the suction. And for the last 2 categories, if the object is close to the center of the box, we will use the gripper to grasp it. Otherwise, we will use the suction. So the main loop is that for each object in the grasping sequence, first we will check the target visibility and choose between grasping and decluttering. Then we will perform the grasping primitive. Also, if the object is occluded, we will use some declutter strategy, which will be introduced later. Then we will check the grasping result, and we will retry detection and grasping if it's not a success. Finally, after 2 failed attempts, we will skip the current target. The declutter strategy of our competition is as follows. The intuition of the strategy is that bigger objects are more likely to create occlusion. So first, we just remove the biggest object, which is determined by the size, and place it in the box corner. But the problem is that a wrong placement will make further picking harder. So we change the method and pick the biggest object, hold it in the hand, and detect the target object. If the target is not detected, we will just put it back. But there is another problem that the biggest one is not always the best to choose among. So the version 3 set a score mechanism considering the size, the mask, and the depth, because intuitively, the object on the top is more likely to create occlusion. So we will just declutter the object with the highest score. But it's still not very developed, because now we just manually design the weights among the 3 metrics. So in the competition, we use a simplified version that removes the objects causing the most occlusion and place it into another box. The challenges we face in the competition are as follows. For the perception part, the object detection without VLMs is vulnerable, and it's hard to adapt to novel objects. For the planning part, for those objects which are close to the box wall, it will be hard to plan a collision-free trajectory. And also, the biggest challenge is that the target occlusion. When only a small part of the object is exposed, it's hard to generate feasible grasp or section poses using the existing methods. And also, when the object is occluded, the declutter algorithms with efficiency and robustness is needed. We have some thoughts for the further development of the decluttering strategy. When people pick inclutter and declutter, sometimes people just declutter with randomness, such as randomly rummaging the whole box. And also, people has prior information on the 3D object geometries, where a small part of the objects leads to an accurate location of the whole object. So a manual design policy is not likely to outperform policy with randomness or train with big data. So there may be more feasible solution is a learning-based policy, training the simulation clutter scene. That's the end of our introduction. Thank you for watching and listening.